Hi, I'm Brian Prier, tutoring high school physics. Today's topic, Young's double-slit experiment. This is a famous experiment that you're probably going to run across in your textbook. Here's what happened. Young set up a wall and then a barrier. The barrier had two slits in it that were extraordinarily small, so small that they were about on the same length as the wavelength of light. And then he shone light through those two slits. You might expect that light would come and pass through in two beams, like so, and then strike the wall at these 2 points. That's not actually what happened. The slits were so small that light instead diffracted, which basically means bent around those slits, something like this. And so we could keep going expanding that out, and basically the entire wall is going to be struck. But it's not all going to be covered in light. You'll notice that the two light waves are going to interfere with each other. And so we're going to get some positive interference and some negative interference. So, here's what happens. Here in the middle of the wall we get a very bright spot. And in the center of that middle we get something known as the central maximum. Around this particular light section we're going to get two dark sections, one on either side, and then we're going to follow that up with another light section, followed by a dark section, followed by a light section, so on and so forth. The center of each of these light sections is also known as a maximum, and so up here we get the first maximum, down here we get the negative first maximum, and so then we'll get the second maximum, the negative second maximum, so on and so forth, as long as your wall extends. We can actually find out where those maximums are relative to the central maximum using this equation. This equation will give us the distance that our maximum is from the central maximum. So, this equation says that the distance for the mth maximum is equal to m times lambda, which is the wavelength of light, times the distance between your wall and your barrier, times the distance between the two slits. So let's work out the distance that the second maximum has from the central maximum for this particular set. So y sub 2, because we're finding the second maximum. Now keep in mind that it's the positive second maximum, not the negative second maximum. 2 times a wavelength of 780 nanometers, or 7.8 times 10 to the negative 7th meters. 7.8 times 10 to the negative 7th. I'm keeping everything in meters so that we don't mess up our units. Times the length of 2 meters. And the distance between slits is 6 millimeters, or 6 times 10 to the negative 3rd meters. Okay, so there's some stuff to go through. If you run that through the calculator, you end up with 2 times 2.6 times 10 to the negative 4 meters. And so then we just multiply that by 2 and we get 5.2 times 10 to the negative 4th meters from our central maximum. So if this here is our central maximum and we go upwards, 5.2 times 10 to the negative 4 meters, we'll find the second maximum. Alright, to recap. Young's double-slit experiment is performed with two slits in a barrier and one wall on the other side. Light is shown through those two slits, and then it diffracts, bends around those slits. The two beams of light will then interfere each other, creating a pattern of light and dark on the wall opposite the two slits. Right in the center, you're going to have a beam of light, which is going to be the central maximum. On either side is going to be a bit of darkness, and then you'll have another maximum. If you're going upwards, you'll have positive maximums. If you're going downwards, you'll have negative maximums. You can calculate where these maximums are relative to the central maximum using the equation y sub m, the distance from the central maximum of the mth maximum, is equivalent to m times lambda, the wavelength of light, times L, the distance between your barrier and the wall, divided by d, the distance between the two slits. Alright, that's all for now. Again, I'm Brian Prier. See you next time.